Welcome. In this video, I'm going to go over solutions from problem set 4.3. So problem set 4.3 focuses a lot on drawing Lewis structures, which then allows us to determine shape and bond angles. So starting with 14, A asks for the Lewis structures of the following. So my typical method, or algorithm if you want to think of it, is to add up my valence electrons. So 1 plus 7 is a total of 8. I draw my skeleton structure using single bonds and then fill in any lone pairs needed, and I count and see how many electrons I've used. So drawing HF with a single bond uses 8 electrons, which is exactly what I had, so this apparently is the correct structure. For B, I have carbon, I have 3 fluorine, and I have a chlorine, so when I add it up, I have 32 electrons to use. When I put the carbon in the middle and attach the 3 fluorine, 1 chlorine, and then I fill in my lone pair. I have a lone pair up here, so 6 on each of these atoms attached to the center atom, but carbon has enough, and I count up, and again, I've used 32 electrons, so that is my complete structure. C, with C2H6, I've got 4 in each carbon, plus 1 in each hydrogen, so this time I've got 8 plus 6, I've got 14 electrons. And now when I draw a single bond to join my 2 center carbon atoms, attach my hydrogen, I would need 2 lone pair on each carbon, and now when I count up, I've used 2, 4, 6, 8, 10, 12. I've used 14 electrons, and I have 14 electrons. So again, this is my correct structure. No double bonds are needed. For D, PCl3, and slide this down, PCl3 for D, I've got 5 for P. The Cl3, I've got 3 fluorines at 7 each, so I've got a total of 26 electrons. So if I put the P in the center, attach the chlorines, each chlorine will need 3 lone pair or 6 more electrons, and the fluorine or the phosphorus will also need 2 more. So when I count up, I've got 8 around each chlorine for 24. The phosphorus then makes 26, and this is my correct structure. E, I had C2H4, so now I've got 2 times 4 plus 4 times 1. I've got 12 electrons, and when I attach my carbons, I've got 2 carbons on each, and I still need 2 more. So I've got 2, 4, 6, 8, 10, 12. I've got 14 electrons, and I only have 12 available. So that means I need to free up 2 more electrons or make 1 more bond. So if I do that, I would redraw this as C double bonded to itself with 2 hydrogen attached to each. And I've used 2, 4, 6, 8, 10, 12 electrons total and created a stable arrangement. Just looking back up to C here and realized it said C6. So I should actually have, even though this worked out numerically, it is not the correct structure. I need to have a hydrogen here, a hydrogen here, a hydrogen here, and a hydrogen here. So again, I've used 2, 4, 6, 8, 10, 12. I've used 14 electrons, but now I've put all 6 hydrogen on. For number 15, how many valence electrons are in the following molecules? This one's pretty straightforward, pretty easy. If I look up BE, it's got 2. I've got 2 chlorine with 7 each, so we're talking a total of 16 electrons. B, I've got boron with 3. I've got 3 chloron with 7 each, so that would be 24 electrons. C, I've got carbon with 4, plus 4 chlorine with 7 each, so this should be 32 electrons. And D, I've got pH3, so I've got 5 from the phosphorus and 1 from each hydrogen for a total of 8. And E, I've got 5 from the nitrogen plus 3 times 7 for the chlorine is a total of 26. In question 18, you're being asked to predict the shape and bond angle of the following molecules. The only way I know how to do it is to actually draw it. I mean, you can make a pretty good guess looking at the formula, but you never know when you're going to, forget about a lone pair and screw it up. So to me, it's quickest just to draw it and be sure I'm thinking about it in the correct way. So when I draw H2S, when I look at the center atom, sulfur's got 4 what IB likes to call electron domains around it, 2 bonding, 2 lone pair. So this means if they were all atoms, that would be a tetrahedral shape. But because 2 of them are lone pair, instead we call this a bent shape, and sometimes it's even called double bent or a V shape. And if it was all equal, if each bond angle was equal between each pair of electrons, then it would be 109.5. But because 2 of them are lone pair, they're going to crowd the hydrogen quite a bit closer together, and that's going to decrease to 105 degrees. With B, with CF4, this is tetrahedral, and I didn't draw in the lone pairs on the hydrogen. I would have to count those to be sure I've bounded this correctly, but it's only the lone pair on the carbon that we care about. So tetrahedral with 4 things attached is going to have the expected bond angle of 109.5. C, I've got 2 things attached, a single and a triple bond, so I've got no lone pair on carbon, so this is simply linear with a 180-degree bond angle. D, I've got 4 domains, 3 are atoms and 1's a lone pair. So this is going to be considered trigonal pyramidal. And if there had been 4 fluorines attached, it'd be 109.5. But since there's 1 lone pair, it's going to squeeze us to 107 degrees between each F and F angle. E, I've got 3 chlorines attached to the boron, but no lone pair because boron's too small to make a double bond, and there's not another pair of electrons available to fill that 4th orbital. So this is going to be trigonal planar, and because there are just the 3 electron domains, it is going to be 120 degrees. And F, I again have 3 pairs attached. As I'm looking, I see I misdrew this. I only have 2 hydrogens attached. I don't know if it'll let me erase this at this point, so let me just cross it off instead. I have 2 hydrogens attached, and this would actually be a lone pair here. So it's got 4 domains, but one of them's got a lone pair, so this is going to be trigonal pyramidal. And with 1 lone pair, that's going to make it 107 degrees. And then when I go down to OF2, OF2 has got 4 electron domains, but only 2 atoms attached. So this is going to be considered bent. And because it would be 109.5 if there were 4 shared pair, it is going to be bent to 105 degrees. Number 19 wants you to predict the shape and bond angles of the following ions. So similarly, again, you need to draw the structures first. So now that I have the structures in for each of these molecules, we can go ahead and start looking at the shape. In A, there's 3 electron domains and all are shared pairs. So this is going to make it trigonal planar. And that means the bond angle is 120 degrees. B is a very similar shape. Again, it's just nitrogen replacing the carbon in the center, but no lone pairs, 3 electron domains. So this is also trigonal planar and 120 degrees. C, NO2, because it's NO2 plus, I've got 5 plus 12 is 17, minus 1 is just 16 electrons. So I end up with nitrogen double bonded to each oxygen, making it linear with a bond angle of 180 degrees. D, now that it's NO2 minus, now I have 18 electrons, so I only need a double bond on one of the oxygen, a single on the other, which leaves a lone pair on the nitrogen and makes this a bent molecule. And this molecule has 3 electron domains, so this is going to be bent at 117 degrees because it would be 120 if all of these were, if the three domains were all shared pair, but since one is a lone pair, that gives it that slightly less than 120 or 117. E, I guess I can't really do that. So I'll just hang on to it here. I'll squeeze this in. E, I got ClF2. I've got 4 electron domains, 2 shared and 2 bonding. So that means this has got a tetrahedral shape according to the electron domains, but this is bent the way we look at it, and it's not only bent, but it's bent twice. So rather than being the 109.5 of a tetrahedral, it's only going to be 105. And then finally, SnCl3, I end up with, again, a tetrahedral domain as far as the electron domains go, but it's going to be considered trigonal pyramidal. And instead of being pyramidal, I think I've got that spelt wrong, but you get the idea. And instead of being 109.5, this is going to be around 107 since there's just the one lone pair. Number 20 is a good question to make sure you're understanding the difference between electron domains and the actual shape of an atom. So if something has a tetrahedral shape, that means it's got 4 shared pair and no lone pairs, or a total of 4 electron domains. So 4 shared, 0 lone, total of 4. B, bent, this actually has more than one possibility because you could have a tetrahedral shape with 2 lone pair and 2 shared pair for a total of 4. Or you could have a trigonal planar domain that has, not 3, but it's got 2 shared pair and just the 1 lone pair, which also would make it bent, and now you just have 3 domains. Or the other possibility is it could be tetrahedral with 3 shared pair and 1 lone. So 3 or 4 are both possibilities because this one is sometimes called double bent and has a bond angle of 105, whereas this one with just 1 lone pair out of the 4 is 107, I'm sorry. But if it only has 3 electron domains and it's bent, this is going to be 117. So 3 possibilities on bent. Linear, that's only going to have 2 things attached to it, 2 shared pairs attached to it. So it could be just the 2 with no lone pair. Linear can also have just 1 shared pair, and then you could have 1, 2, or 3 lone pairs on it. So the book says just 2 because they're thinking of a linear as in CO like this, where you've got 2 shared pair and no lone pair. But you can have a linear atom such as HF, and this actually has 4 electron domains. You could have HO minus, which would have, well, that's actually going to be the same, but you get the idea that if you only have 2 in your linear arrangement, it's possible to have 1, 2, or 3 lone pairs on that second atom, especially when it's attached to hydrogen. So I think they're referring to when you truly have a center atom in this first case, but it's fair to say there's other examples as well. C then, that was C. D, trigonal pyramidal, that has to have 4 things attached. It has 3 shared pair and 1 lone pair, so there's 4 electron domains. And trigonal planar has 3 and 0 for a total of 3 electron domains. In number 21, you're supposed to predict whether the following will be polar or nonpolar molecules. Well, the first requirement is that you have polar bonds. And then if you have polar bonds, you have to look at the shape of the molecule and what's actually attached to it. So pH3, I'm going to have polar bonds, and so I have to look at the shape, and I see that there's a lone pair on the phosphorus. So because of the trigonal pyramidal shape, I am going to have a polar molecule. B, I may have polar bonds, but the tetrahedral shape is going to balance the charge, so this is going to be a nonpolar molecule. C, I didn't even bother drawing because it doesn't matter. With HCN, I've got two different kinds of polar bonds, so whether this is linear or bent, I am definitely going to have a polar molecule here. BeCl2, this is an exception because you would expect a double bond to fill this up, but Be is too small for double bonds. Either way, it leaves Be with no lone pair and the same type of atom bonded to each side, so this is linear and nonpolar. C2H4, the double bond in the center doesn't really matter, but this is going to be nonpolar as well, as many hydrocarbons are. It's very symmetrical. CLF, even though this is linear with just two because they're not the same kind of atom, this one is going to be polar. F2, nonpolar because there's no polarity in the bonds. And BF3, again, boron's too small to make a double bond, but there is no lone pair on boron either. So this is going to be trigonal planar and nonpolar. Number 22, the molecule C2H2Cl2 can exist as two forms known as Sis Trans Isomers. And if you take a look, you can see what it means. The chlorine and hydrogen can be opposite from their like atom, or they can be on the same side as their like atom. And it says determine whether either of these has a net dipole moment. So the first one, the one on the left, I should say, is called the trans because they're across from each other. Cis I always think of as same side. Cis kind of sounds like side. I don't know, that's how I remember. But in this case, the chlorine and chlorine are like opposite of each other in a tug of war, and the hydrogen are across from each other in the tug of war. And this carbon atom, if this was a single bond, this could just as easily flip up here and flip down there, so there would be no discussion. But because it's a double bond, it can't flip. So the chlorine pulls electrons this direction. I believe the carbon pulls them slightly from the hydrogen. But there's going to be no polarity here because the net movement is the same direction. Is opposite directions. But over here with the cis, now I've got the chlorine pulling this way, making this end more negative. I've got the hydrogen losing control, making this end positive. So this one does have a net dipole, whereas over here I've got negative, positive, so I don't have a true positive and negative tail. So only the second one is going to be considered to have a net dipole moment, or the cis configuration. 23, put the following species in order of increasing carbon-oxygen bond length. So you have to realize that CO has a triple bond and is the shortest. CO2 has two double bonds. CO3 has this resonance, so this is triple, double. Because this resonates, it's like 1 1/3 because it's resonating between three places. And then the CH3 OH is going to be a single. So it's nice they put them right in order for you. Increasing carbon bond length, this is it right here. This is going to be the shortest at a triple, then the double, then the resonating bond, and then the single will be the longest. Number 24, by reference to the resonance structures, compare the nitrogen-oxygen bond lengths in nitrate 4, or nitrate 5, I'm sorry, NO3 minus, and HNO3. So I'm going to have to go ahead and draw these structures. So looking at the structures, NO3 is going to have resonance because it needs one bond, the nitrate. Whereas once that nitrate bonds with hydrogen, now there's no longer a double bond anywhere in the structure, so it's just a 1.0 or a single bond. So the bond length is going to be, the nitrate is going to have a slightly longer bond than the nitric acid. Number 25 and 26 are talking about carbon, especially, and the different allotropes or forms of carbon. And this is stuff that you just kind of have to memorize, or you just realize you're going to forfeit a couple of these points when you take paper 2. Paper 1, you at least have a chance to maybe recognize the answer. But 25, similarities between silicon and diamond. They both have these giant covalent structures, so they have high melting points. They're very hard and rigid. They're non-conductors, at least of electricity. They also tend to be insoluble in water. They actually can conduct heat, thermal conductors, although they're not like fantastic, they're decent. Differences are diamond is stronger. Most of you know diamonds are incredibly strong. Also, it's more lustrous. A lot of its value is the way it shimmers and shines. And silicone can be converted, or what they call doped. You add impurities to it to become a good conductor, which is why we use them in computer chips. And then 26, explain why graphite and graphene are good conductors, whereas diamond is not. Well, good conductors have delocalized electrons. So for whatever reason, the way graphite and graphene are bonded, they're more of a two-dimensional structure. The electrons are free to move at least in one plane, whereas diamond is a very rigid 3D structure and does not have these delocalized electrons, so is not a good conductor of electricity. Number 3, what's the correct order of increasing boiling points? So what you're really looking for here is polarity. So each of these molecules has a CH3 group with something else attached to it. CH3 with another CH3 group. This one's got CH3, CH2, and then a Cl. So we're looking at the difference between a hydrogen, a chlorine, a bromine, and an iodine. So what does that do to the polarity? Well, this is going to be nonpolar because this is going to be balanced around with two CH3 groups. Chlorine, bromine, and iodine, if I look at it, this is going to be the least polar. This is going to be the most electronegative or most, and this is going to be in the middle. So as far as increasing boiling points, HCl, the Cl is going to be the highest, the H is going to be the lowest. So if I look for it here, the best choice is A, but they actually have these two reversed because chlorine is more electronegative, being the smaller. So it's going to have a greater polarity than the iodine will. But I hadn't noticed that before. Now, there really isn't a correct answer, but that's the closest you get. And then 4, which compound forms hydrogen bonds in the liquid state? So hydrogen bonds form between oxygen and hydrogen. They're the fun atoms. So oxygen, hydrogen, or hydrogen and nitrogen, or hydrogen and fluorine. Any of those should be able to form a hydrogen bond, depending upon how the structure is set up. You have to be kind of careful when you look at it and make sure the hydrogen and nitrogen are actually bonded together, not just in the same compound. So in this case, although it looks like all but B would be capable of a hydrogen bond, the only one where the oxygen and hydrogen actually bond together is in A with the OH group. With the N, the carbons are attached to it, so there's no direct NH bonding. And with the CHO, that's telling you that the hydrogen and oxygen are bonded separately, like so, to the CH3 group. And again, this is more organic stuff, which we're moving into next. So just a preview of what's to come. Number 5, which species contains a coordinate covalent bond? So you'd have to do some sketching here to know. But CO is going to be a triple bond, and then carbon and oxygen would each have a lone pair. That's because oxygen donates both pairs, so CO is a coordinate covalent bond. And H3O, this is one that came up on an earlier problem. You have H2O like so, and then the H plus comes in and forms a coordinate covalent bond. So C, 2 and 3 only would be the correct choice. Number 8, which model, according to Vesper theory, would be expected to have the smallest bond? So when I look at this, H2O is going to be bent. In fact, it's going to be double bent at 105. pH3 is going to be trigonal planar, trigonal pyramidal. So this is going to be around 107. CCl4 is going to be 109.5 because it's a true tetrahedral. And H2CO is going to be 120. So A, the double bent, is going to have the smallest bond angle. And again, you just have to draw them. And when you've drawn them a long time, they come more quickly. Number 11, which is the best description of the carbonate ion? So I've got CO3, 2 minus. So I've got 4 plus 3 times 6, 18, 22. I've got 24 electrons. So this is going to bond with, like so, with 8 around each electron for a total of 24 and no lone pair on the carbon. So this is going to be planar triangular or trigonal planar, and the bond angle is going to be 120. Number 12, which molecule contains polar bonds but is nonpolar? Well, I can eliminate A and D right away because they're bonding to like atoms. So then CCl4 is going to be tetrahedral with the 4 chlorine, and NH3 is going to have a lone pair. So even though it's got polar bonds, the tetrahedral shape makes it a nonpolar molecule. And 14, which substance can form intermolecular hydrogen bonds in the liquid state? So again, this is getting ahead of us a little bit with organic, but CH3OH is going to have the 3 carbons with the oxygen between. So none of that, the oxygen isn't bonded with any of those hydrogens. The CH3CHO is telling me there's going to be an H up there, and then the oxygen's double bonded. So again, with C, it's not actually bonded between the oxygen and hydrogen. B, the CH3CH2, and then the OH, there I've actually got an opportunity for a hydrogen bond, and D doesn't even have any of the fun atoms, fluorine, oxygen, or nitrogen in it. So B can form the hydrogen bond in the liquid state.